Well, I've pulled up MATLAB here, and here's a script that I'm going to use. I want to explain what we're doing. I want to look at something that we know what happens in this particular case. So we're going to look at an ideal second order response, and we're going to take a look at different values of zeta and show how to make this plot in MATLAB. And the reason I'm doing it this way is I want to add in different effects, like a nearby real zero or a nearby real pole, and we can take a look at how the overall response changes in those situations. Okay, so right now what this is the ideal second order response. Okay, and I'm using a transfer function object. So the first line I have here is S is equal to TF, open parentheses, and then in single quotes the letter S. That makes S automatically be a transfer function object. So when I define something like a transfer function here, I'm going to call it H2, all right? I can then take a look at the step response using H2, using the built-in object function called step. Okay, so you see here, we're doing a step response, and this has this stop at normalized time equal to 40, so we can get all of our plots on the same scale. And then H2 is what's holding our transfer function. So we're looking at the step response of an ideal second order system as a function of zeta. Okay, so you notice what I've done here is I put it in a for loop. Okay, so we're looking at various values of alpha, and I've set up those values to be here. All right. The next thing I wanted to show you is I can make a plot, and I can mess with the parameters of this plot. I didn't like the line thickness, so I can make it thicker. I also wanted to add a legend so you can see where the different values of zeta show up. So you can use that in MATLAB with a field called display name. Okay, and in display name I can then print that. Sorry, trying to slide that over. I can use a string print kind of command, just like you would, similar to C, but a little bit differently formatted. And I can use a double backslash to give me actually a LaTeX version of zeta. So this should show up with the Greek letter zeta, and it's going to show up with 2 decimal places. All right, so you'll see when we run this. The other thing I wanted to do is be able to talk about this as it evolves, so I'm putting a pause into the plot process, and so it'll make an initial plot, and then we can talk about what happens as zeta changes, and the legend should get updated as we go. Okay, so let me run this, and you'll see what I'm talking about. Okay, so I run this. Initially, zeta equals 0 gives me a cosine or a sinusoid. And you can see different values of zeta. The damping is starting to come down, and by the time I get out to zeta equal 0.7 and 0.9, there's very little overshoot and very little ringing. Okay, so you already had seen this. This is a plot that we talked about before. You look at the damping factor zeta equals 0, no damping at all. It looks like a sinusoid. Zeta close to 1, you get well, at zeta equal 1, you get a critically damped response. Okay, so those are step responses. We can take a look at pole locations. We understand how that works. We've seen that diagram, and we can go from there. All right, so use this as sort of the basis of subsequent discussions that we're going to have about step responses given different pole and zero configurations.